All right. Hello. Good evening to you all. Can you hear me?
Yes, we can hear you.
Yes, I
Yes,
can.
please. Yes, please.
Yeah, we can hear you.
We are about to commence. You are all welcome to JP Academy Guitar Lessons, where we teach people how to translate from an absolute beginner to a specialist or a professional in the design, analysis, and protection of power systems using ETAP software. So, once again, you are all welcome to this session. And before we proceed, I would like to give honor to some distinguished persons. And I can see the president of the chairman of NIEEE, Nigerian Institute of Electrical and Electronics Engineers, Calabar chapter, who we are partnering with for this presentation. So I would like to invite Engineer Dr. Kazim Ujikutu for an opening remark. Engineer Dr. Kazim. Okay, since it's having some challenges. All right. Once again, you all are welcome to JP Academy ETAP sessions. And as we established earlier, this session will be a 2-day session. We're going to have one today and one tomorrow, same time. And it's going to be a 1-hour session. So, all right, he's having issue with his audio. So, no problem, you can carry on. So the session is going to be from 8 p.m. to 9 p.m. today. Today we are going to have an introductory class. We are going to be introducing the concept or the principles of power system protection using ETAP software. And tomorrow we are going to have a more practical approach on that. So let's begin. I'm going to share my screen so I can use slides. Yes, this session will be recorded. It is being recorded as we speak. All right, let me know when you can see my screen.
I can see your screen from here.
All right. So let's begin. As I said, we are going to be discussing the principles of power system protection using ETAP software. And we are partnering with the Nigerian Institute of Electrical and Electronics Engineers, Calabar chapter. So I am going to be your presenter, and my name is Ekwe Peremobore Jesse, and we will be discussing the principles of power system protection. So we are going to be following a guide to enable simplicity, and we are going to begin with the concept of power system protection. What is this power system protection all about? Then we move into the qualities of a protective relay. Then we talk about protection zones in electrical power systems. Then we move on to protection schemes. And we are going to start a brief explanation on the concept of what an overcurrent protection scheme is all about. After that, for our overcurrent protection scheme, we are going to require CT ratio calculation. We are also going to require relay pickup settings calculation. Then we'll move into proper relay coordination and we conclude. So this is basically going to be our outline for these sessions. So we start with the introduction. What is power system protection? What is power system protection? So basically, power system protection is the act of employing a mechanism in order to ascertain or determine mitigation in the effects of faults occurring in our power system network. Now, aside what power system protection is all about, how about we look at why we need power system protection? What what really introduces power system protection? So once we are having our power system, in our power system network, one thing is inevitable, and that is the introduction of fault. Regardless of how much you into your power system, regardless of you buying the most efficient and expensive equipment in your power system, faults are inevitable. Be it symmetrical or asymmetrical faults. Please mute your microphone so we don't have interruption. Someone pick it up. So faults are inevitable, and this gives rise to the need for power system protection. In our power system, we have equipment such as our alternators, our generators, our capacitors, our bus bars, our transformers. And each of these equipment are to faults. It's inevitable. One way or another, they are going to experience a fault event. So the objectives of power system protection is simple. When a fault arises, isolate the fault. But it doesn't stop there. When a fault arises, good and fine, we are isolating the fault. But then we need to ensure that we are isolating only the fault, not just isolating the fault. We need to make sure we are isolating only the fault. That's the second objective. The third objective is while we are isolating only the fault, we should ensure that we are isolating only the fault as quick as possible. Those are three objectives. I usually give four. Now, this fourth objective is this. In as much as we are isolating the fault, we are isolating only the fault as quick as possible. We should ensure that we are isolating the smallest unhealthy portion, meaning we should ensure we are reducing the loss of continuity in the system as much as possible. So these are the four objectives. Firstly, we need to ensure we are isolating the fault. Secondly, we need to ensure we are isolating only the fault. Thirdly, we need to ensure that we are isolating only the fault as quick as possible. And lastly, we need to ensure that we are isolating the smallest unhealthy portion of the system. Now, basically, in electrical power systems, protection is mainly carried out using protective relays in conjunction with our CTs, that's the current transformers or voltage transformers, and then with our circuit breakers, basically, for basic form of protection. So if we are using our current or voltage transformers, basically a current or voltage transformer is changing the transformation ratio of either current or voltage. And by that I mean our current transformer stepping up or stepping down current, voltage transformer stepping up or stepping down current, stepping down voltage rather. And circuit breakers are our switch gears, such as our SF6 circuit breakers, air circuit breakers, miniature, all of that. So basically, we are going to be using our protective relays in conjunction with our measuring instruments, which is our current or voltage transformer, and our circuit breaker. Next, we are looking to basic requirements of a protective relay. What are these qualities that a protective relay should possess before we can say that this protective relay is efficient? There are certain criteria that this relay must possess. And the first one of these criteria is that a protective relay must possess reliability. Now, reliability is the most essential requisite of a protective relay. And why I say this is, reliability is a degree of certainty that a relay will operate correctly as at when required. Because these relays usually remain inoperative until a fault is introduced to the power system. Now remember, the work of this relay, it is a protective relay. It is only to function when there is a fault in the system. And a fault in the power system does not occur every minute. It can be once in a day, it can be once in 2 weeks, it can be once in a month, once in 3 months. So it is crucial that we are sure once there is the introduction of a fault, then the relay should instantly pick up. So that degree of certainty that the relay will operate is what we call reliability. The second quality we have is selectivity. Now, selectivity is a measure of how well this protective relay limits the loss of continuity by isolating the smallest unhealthy part of the electrical network before it spreads into the healthy part. Now, if you come back to our objectives of power system protection, we said it's to isolate the fault. However, not just isolating the fault, isolating only the fault. This is where selectivity comes in. It should know, it should be able to detect the exact section in which the fault is occurring and isolate only that section, not the entire system. This is where selectivity comes in. Now, the next essential quality is speed. Now, usually when I say a relay should have speed, someone would want to say, okay, the relay should operate instantaneously or very fast. Now, that is a wrong concept. When we talk of speed in protective relay, the protective relay should neither be too slow, because if it is too slow, it will lead to damage of our equipment. But then, when a fault is introduced, it should also not be too fast, because if it is too fast, it may result in an undesired operation, such as the relay in the healthy part issuing a trip command before the relay in the unhealthy part. So this is going to increase loss of selectivity if the relay speed is too fast. Now, in order to maintain stability in the power system and reduce or limit the loss of continuity, the relay should operate by isolating the faulted areas as fast as possible. Yes, it should operate fast, but then it should not operate too fast. Yes, it should not operate too fast, but then it should not operate too slow. It should operate as at when required. Next, We have simplicity. Now, simplicity is an essential quality generally, even in electrical engineering. In power systems, sure, easy, and fast troubleshooting, simplicity is the key. Now, I usually say simplicity is the ultimate sophistication. It's the quote I picked up. If a fault arises, if you should design a system such that when a fault arises, the only person that can identify that fault is you, then you have designed the wrong system. If you should design a system such that the only person that can pick up the drawing and understand the drawing is you, then you have designed the wrong system. It should be simple enough such that anybody can easily pick it up and know, okay, this is this. Because there are multiple scenarios that can come up where you will not be around. You will be unavailable at the moment. You can't be everywhere at once. So because of that, if another person cannot pick it up and understand it, then the whole system is compromised simply because you are unavailable. So for easy and fast troubleshooting, simplicity is a key. Now, this brings us to the last essential quality of a protective unit. This is sensitivity. Now, a protective unit must be proficient enough to detect when its actuating parameter is exceeded. Thereby, it will issue a trip command to its circuit breaker that is on alert. Now, when we say actuating parameters are simply set levels. For example, if we say the current should not go above 1000 amps, and we program this so that it should issue a trip signal once the current is above 1000 amps. The relay should be sensitive enough, should be proficient enough to detect precisely 1001 amps. Once it is above the set point, the relay should be able to detect it instantaneously. That is what sensitivity is all about. So, next we'll be moving on to protection zones. Basically, what is a protection zone? A protection zone is a part of the power system network that is protected by a particular type of protection scheme. Sounds quite complex. A protection zone protected by a particular type of protection scheme. So, what we mean is this is usually set up around each equipment in the power system network. So when a fault is introduced in the power system, only the circuit breakers in that zone of the equipment will be open, thereby isolating the other device. We'll get there. When we talk about protection schemes, using a particular type of protection scheme, what we mean is this. A protection scheme or a protective scheme is a method of power system protection employed for a particular type of power system apparatus. So if we say, okay, we have a particular type of protection for our transformer, we have a particular type of protection for our transmission line, we have another type of protection for our feeders, for our bus bars, for our generators. Those are protective schemes. Then the area these protective schemes are operating is known as a protection zone. Whatever equipment or range of equipment a particular protective scheme is covering is known as a protection zone. So we can have a transformer protection zone. We can have a transmission line zone. We can have our generator zone. We can have our feeder zone. So once we are protecting a group of equipment or a single equipment with a particular type of protection scheme, then it is known as a protection zone. And the aim of this protective scheme is to isolate a faulty section from the healthy section in order to ensure continuity of power supply without any severe damage arising from the introduction of the fault. So basically in electrical power systems, we have multiple protection schemes. We have the overcurrent protection scheme, we have the differential protection scheme, we have the distance protection scheme, and all that. So let's start from the concept of an overcurrent protection scheme. When we talk about overcurrent, as the name implies, once the current is above the set point, it is termed overcurrent. So a transient change in current can actually be regarded as an effect of a fault. So overcurrent protection can be said to be the most widely used principle of protection because the magnitude of current can be utilized as an indication of the source impedance. Also, it is used due to its inherent simplicity. It is quite very simple. Now, basically, overcurrent protection requires the overcurrent relay, the current transformer, and a circuit breaker. As simple as that. So, an overcurrent relay, current transformer, and then a circuit breaker. Now, the protective relay is the one actuating the circuit breaker. The circuit breaker will be interlocked to the protective relay, and then the current transformer is used to measure, to compare, okay, what's the current flowing here? Is it above my set point? Is it below my set point? If it is above my set point, okay, I'll send the information to the protective relay. The protective relay will send the information to the circuit breaker. That is basically how the overcurrent protection scheme works. Now, when we say overcurrent protection scheme, we have basically two types of overcurrent protection scheme. The first is the instantaneous overcurrent protection scheme, and its code is 50. While the second is the time overcurrent protection scheme, and its code is 51. So usually, people call overcurrent protection scheme 5051. We can add an N for at fault. Now, 50 is instantaneous protection, 51 is time overcurrent protection. And as the name implies, instantaneous. That's the difference between both of them. Instantaneous is as soon as there's a fault, the relay should operate. Time overcurrent is okay, there's a fault, there should be time difference between the relays. Now, I would like to clarify something. When we say instantaneous protection, when we say this relay is operating instantaneously, we do not mean that the very instant a fault occurs, the relay is operating. No. We do not mean that the very instant a fault is occurring, the circuit breaker is opening. No. In instantaneous protection, we are saying that we designing the protection scheme, do not put any intentional time delay. There is no intentional time delay. However, there is time delay. Now, what causes this time delay? This time delay is caused by the relay operating time, the circuit breaker operating time. Now, when this current transformer identifies that, okay, this current flowing in this circuit is actually above my set point, it translates the information to the relay, the overcurrent relay. Now, for the course of this overcurrent relay to be energized so that it can open its interlocked circuit breaker, a time margin will be considered, maybe 20 milliseconds. Even though it's negligible, there is a time margin. Now, for the course of the circuit breaker to also be energized, to either open or close, there is also a time margin. So it is not happening instantaneously. However, it is happening very fast. So the concept is, we do not put any intentional time delay when it comes to instantaneous protection. But then there is time delay. But when it comes to time over current protection, we actually put intentional time delay. Now, let me give an illustration. If we are using, maybe, let's say, to start our motors, we are using our direct online starters, and we know that for our direct online starters, we can use up to 6 to 8 times the nominal rated current for a few seconds. There will be this high inrush of current, and if we are using that to start our motors, and let's say the motor requires, let's say, 600 amps, a 600 amps motor using direct online starter, and then we put our instantaneous overcurrent protection. Let's say we say, okay, if the current should get above 1,000 amps, it should trip. It should allow its nominal rated 600 amps. Now, using our direct online starter, we are saying that as soon as this motor should start, the relay should issue a trip signal. So as the motor starts, the relay will turn off the motor. As the motor starts, the relay will open the breaker, isolating the motor. As the motor starts, the relay and will continue in that cycle. But then, if we come over to time over current, we can say, okay, when this motor starts, yes, the set point is 600 amps. Sorry, 1,000 amps. The nominal current is 600 amps. But then, if you should see anything above the set point, which is 1,000 amps, ignore it for about 5 seconds or 2.5 milliseconds, or depending on the time, motor starting time. Ignore it for this specified period of time. If after this time, this margin set has elapsed and the motor is still running on a current above 1,000 amps, then trip. This is where time over current protection comes in. So instantaneous protection, we cannot use it for direct online because it will trip, unless we have to increase our set point, which could damage our motor. Now, this is the basic difference between instantaneous protection and time over current protection. And as I mentioned earlier, we have other protections. We have the differential and the distance protection, although we'll be focusing on the overcurrent protection scheme in this webinar. But basically, okay, let me just touch it a bit. We have the differential protection, we have the distance protection schemes, we have the over frequency, under frequency, over voltage, and all that. Now, when it comes to differential protection, it is a unit type of protection scheme, and it is employed for a specific zone or a specific piece of equipment. Differential protection works based on the principle of Kirchhoff's current law. The sum of current leaving a node is equivalent to the sum of current entering the node. So it is usually employed on equipment such as transformers, bus bars, generators, and all that. And it operates on the principle of measuring the input current, then to compare it with the output current, Kirchhoff's current law. Once there are discrepancies, then it knows that there is a fault. That is the principle of operation of differential protection scheme. Then if we come over to distance protection scheme, distance protection is a non-unit system of protection. So basically, distance protection scheme measures impedance. So it measures the impedance between the location of the relay and the point where the fault is incident. Then to compare it with its set values. Once there are discrepancies, it trips. Distance relays are usually employed on very long transmission lines. Now, as I said, for overcurrent protection, we are going to require an overcurrent relay, we are going to require a current transformer, and then we are going to require a circuit breaker. However, we are going to require the input of the CT ratio when it comes to overcurrent relay. We are going to require our relay settings. So we need to actually carry out these calculations to ensure appropriate functions, to ensure efficiency, to ensure reliability. We need to carry out these calculations. So how can we calculate the CT ratio? Now, CT ratio can be calculated using this formula, where we have FLA. FLA is simply the full load current in amperes. Then we are going to add 25% of the full load current in amperes. For example, that 25% is actually safety factor. Now let me give an example. If we have an equipment whose nominal current is 200 amps, and then we want to use a CT, so we are trying to calculate, okay, what should be the CT ratio? We just need to get 25% of the nominal current, that's the full load current in amperes. So since we have identified it is 200 amps, 25% of 200 amps is 50 amps. All we need to do is add that to the nominal current. So our CT ratio will be 250 is to 1. Now we can have CT ratios of 1 and 5. So the ratio will be either is to 1 or is to 5. For instance, we can have the CT ratio of 250 is to 1 or 50 is to 5 for our CT ratios. So basically, we are just adding 25% of our nominal rated current. And this full load current in amperes, it can simply be calculated by getting, okay, assuming it's a load or a transformer, we just identify the MVA rating, the power rating, we divide it by root 3, square root of 3 multiplied by the voltage magnitude. So our CT ratio is basically 125% of our full load current in amperes. Next, we'll be looking at our relay pickup settings. Now, when it comes to relay coordination, Relay coordination is an art, it's not a science. Why I usually say it's an art? Okay, you have called me and 9 other engineers to design a relay coordination scheme. And then we will all design, but we'll have different results. And I can assure you that it's possible that each and every one of us, if you should impute it, if you should simulate and actually use it, it will work. But then our results are not the same. Now, when it comes to pickup settings, we can have exactly the same calculations. We can have exactly the same results because the pickup settings can be mathematically calculated. The pickup settings, we have a science to employ and determine the pickup current. However, when it comes to the time dial settings, TDS or TMS, time multiplier settings, there is no actual standard formula. Okay, just impute this, calculate this, and you get it. No, it doesn't exist. That is where it becomes an art instead of a science. So all 10 of us can get the exact pickup settings, and then when it comes to our TDS, it's going to be different. But it will work. So when it comes to pickup settings, we can calculate it using this formula. Where 1.1 and 0.9 will be our safety factors. So FLA is full load current in amperes, CT sec is the secondary rating of our current transformer. We would actually be using this when we are designing an overcurrent protection scheme. We'll carry out relay coordination and all that. We'll be making use of all this. So today is just more of an introductory section. Now, at this point, it's going to become a bit interactive. We have a relay coordination example. Now we are having a fault at this point, and then we are having trips at this point, then this point, then this point, and it comes over to this point. Is this system properly coordinated? Remember, there is a fault here, so it knocked off all these feeders before isolating the main feeder to the bus bar. So I would like to hear your thoughts. Is this properly coordinated? Should this be the right sequence? Or,
No.
okay, we'll have another example. The fault is still at the same location. This strips ignores this, and this strips. Once this strips is isolating everything here. So we have isolated this part. Remember, there's no fault here. This is where the fault is. So we are automatically isolating this part for a fault at this point. So between these two, which is the right sequence and why? Any idea?
I would say the right sequence is the first diagram.
The first one is okay. Why?
Yeah.
Why do you think that's the right one?
Okay. Because there was before the fault went further to affect the bus bar.
Yeah.
So there was like coordination, relay coordination to protect the bus bar. But in this case, the whole entire bus bar is affected once there is a fault on the relay on the lump load 7. So the entire bus bar is affected. But in this case, the entire bus bar is not yet affected. Only some of the feeders, feeder 2 and 3, are affected.
Okay. Okay. Now, any other idea? Or we all agree with him? Because he actually made sense. This is where the fault is. So why are we rushing to isolate this point? Because once this point is isolated, then these feeders are out. Remember, we have our objective to limit loss of continuity. Any other idea?
Okay. Can I come in here?
Yes, you can.
Yeah. Okay. So I think if I assume that those in green, those breaker in greens means they are going to operate simultaneously, it means that the bus protection and the feeder protection are not coordinated, because the expectation is that the feeder should trip first before the bus. That is the expectation. I'm talking about the one by the right,
Okay.
and so on and so forth. So that's why. Then the left is a no. The left is a no.
Okay.
Thank you.
So none of them is correct.
Oh yes, if green means simultaneous operation, none of them is good.
Okay, they are not operating simultaneously. They are not all green. This is one, two, three, four. They have different colors. They are not all green.
Okay, I can't see the color, but I can now see the number.
Okay.
Okay, so if it is one, okay, I can now see 1, 2, then that's right, is okay.
Okay. Okay.
So I also think that yeah, none of them is okay, especially if we are considering selectivity, because once the breaker at CB9, okay, CB9 operates, it simply means it's shutting down everything, the three feeders. So it's not reflecting the selectivity principle then.
Okay.
But can I just add something, please?
Yes, you can.
So for the first diagram, you can see the breaker CB9, which is lighted by is it orange color. So that means that the bus bar is uh, is operating. The bus bar is still operating. Only that the feeders feeder with lump loads 5, 4, and 7 are not operating at this point. So that means comparably, the two diagrams, if we have to compare them, diagram 1 is still better because we still have a bus bar S4 energized. But in the case of the second diagram, the bus bar loss is like there is no power to the bus bar. So I will still pick the diagram 1. Though both of them in terms of selectivity and protective coordination, they are not good. But I still prefer diagram 1 to 2.
So, but that diagram one, the those two outside the where that is faulted, those two have no business operating. Those two breakers have no business operating. They
Can
have
I
no
can I
business
speak,
operating
sir?
because the fault current is not expected to flow through them. The
Sir,
bus can operate because it can see it as a backup, but these other ones are not supposed to see that fault.
Okay. Okay.
can I, can I say something, sir?
Yes, you can.
Me,
Go ahead. Go ahead.
Anas, I am Anas Hamid. I wanna say it's diagram number 2 is correct.
Yeah. Let me say
Because
something.
Please hang on. All right. Go on.
because because circuit it
Okay, so
One person at a time, please. Please continue.
okay
Sir, I'm Anas Amit. I'm according to my point, my understanding, diagram 2 is correct because it's a feeder breaker is coordinated with the feeding breaker of the bus, and then to the feeding breaker of the transformer, and then to the feeding breaker of the second bus. So diagram 2 is correct according to selectivity and relay coordination.
Okay, for purpose of time, let me wrap it up. Now, you see,
All right. Can I say my piece, please?
okay, 30 seconds, please.
All right. So, as a protection practitioner, I don't think that diagram one is okay uh, because we have that. Unless you tell me, and I've seen that in practice, where you have relays operating sympathetically, and that is as a result of uh, capacitive coupling between feeders, where feeder one operates and feeder two and three goes with it. So that is bad and it's a no-no. And then in respect of diagram number two, if breaker CB, I think that is labeled CB13
Yes, CB4.
and CB89. So if CB13 fails to operate, we expect that CB9 should operate as a backup to CB13, but they should not operate simultaneously.
Yes,
So you know that in terms of when you are coordinating relays, when you have a relay downstream of another relay, one relay acts the relay upstream acts as a backup to the relay downstream.
yes,
So when there is a fault on the CB13, you expect that sorry when there's a fault on lump 7, you expect that CB13 should operate. Now if CB13 fails to operate to clear the fault, you expect that CB9 should operate and clear the fault. If CB9 fails to operate, that is when you expect that CB8 should operate. However, they should not operate simultaneously.
yes. Okay,
CB9 operates first when CB13 fails, and then if CB9 fails too, CB8 should operate. Thank you.
all right. Thank you, thank you. Okay, so just as most of you have said, this on the
Yes.
left is
Can I?
actually wrong. Hello?
Hello.
Yeah, just hang on. Now, this on the left is actually wrong. This on the right is correct. We need to understand that fault isolation is different from relay coordination. I intentionally put this here, relay coordination example. Now, when it comes to relay coordination, we have primary and backup relays, just as the last person mentioned. So, if there is a fault on this feeder and the fault goes up here, and this relay fails to operate this breaker, the fault is not coming here, the fault is coming to this bus. So, if we are saying that when the fault comes here, we should come and be tripping here, we should still come and be tripping here. Before these three breakers will be tripped, we have damaged all these equipment up to this point. Remember, the breakers are not tripping at the same time in relay coordination. They are not tripping at the same time. There's a time margin between each relay to operate. But if we have a fault here, this fails to operate, then this operates as a backup. So this is the primary relay, this is the backup relay. If there's a fault at this point on the bus bar, this becomes the primary relay and this becomes the backup relay. That's the way relay coordination works. So this is wrong and this is correct.
Hello.
Yes, someone
Hello.
will say something. Yes, I
Yeah.
can hear
Okay.
you.
Okay. My name is Dixon.
All right.
Okay. I beg to you ask me, going by the purpose of protection, power system protection,
Yeah.
both of them are not correct.
Okay.
Okay, I'll explain it. I'll give a very simple example. For instance, let's assume we have a patient in an hospital, and that patient is undergoing an operation
Yes.
on lump load 6.
Okay.
Okay. Now a fault occurred at lump load 7.
Yeah.
Look at the coordination for both sides, both picture 1 and 2. The patient in lump load 6 dead with the arrangement.
Okay.
Meanwhile, in relay coordination, we expect that the breaker, closest to the fault should operate, just to make sure that a fault in a remote area should not affect the other area. If
Selectivity.
you look at these two pictures, both of them affect the other area. So at the end of the day, lump load 6, load 5, lump load 7, all of them are down on both pictures. Two of them does not, respect
All right.
one of the pictures or the purpose of
Let me
relay coordination.
respond to that. Let me respond to that. Now, when I started, I made mention of this. When we say relay coordination is different from fault isolation. What we are seeing in relay coordination is, should in case a particular relay fails to operate, what is the backup relay? That is relay coordination. Fault isolation is, let me identify the precise location of this fault, and then I should isolate only the fault. So if we are looking at fault isolation, we are only going to experience a trip at this point here. We are actually going to see the illustration using ETAP software in tomorrow's session. If we are expecting a fault isolation is for, okay, isolate only the faulted place. Relay coordination, let us see how all the relays in the system will operate one after the other, the primary relay and the backup relay. That is relay coordination. I don't know if the point is clear. Okay. All right. Sorry for the interruption. Can you hear me? Can you hear me? Can anyone hear me?
Yes, we can hear you.
Yes, I can hear you from my hand, please.
Okay. Do this.
Please, before we continue, can we get the soft copy of this lecture after the whole thing?
Yes, yes, you can. I'll share it on the group chat.
Okay, we appreciate that, sir.
All right.
Can I ask a quick question before you continue?
All right. Yes, you can go ahead.
Okay, so in the instantaneous relay and time relay, there's 50 and 51 there. What does those two numbers mean?
Okay, 50 is the 5051 is the, so instead of saying overcurrent protection, we can just say 5051. So 50 is a code, a standard.
Okay, Engineer
Okay.
Jose, can I also ask a question, please,
Yeah.
before we proceed? So my question is, what is the difference between overcurrent and short circuit?
Over,
Because and short circuit
okay.
protection.
Short circuit protection, overcurrent protection. What happens in the case of a short circuit? Let me come from that direction. What happens in the case of a short circuit?
Short circuit is a fault.
Yes, we know short circuit is the fault. So when the fault occurs, what happens in the system?
There is
There is,
also overcurrent, like the current is far larger than the nominal current, and maybe times 6. It's a multiple of nominal current.
Not correct. So, so we are saying that there is an increase.
oh, should go outside.
Overcurrent.
Go outside.
We are saying that overcurrent is protecting against increment of nominal current. So short circuit and overcurrent protection. Overcurrent protection is just a method of limiting an effect of short circuit, limiting the effect of overcurrent. As simple as that.
Excuse me, can I ask for something? Please, can you ask everyone to mute the microphone because we are not able to hear you.
Okay.
Please, if everybody can mute the
Kindly
microphone.
mute your microphones. Okay, I think it's better now. Can everyone?
Yeah, thanks. It is.
Okay. So, as I was saying, the effect of short circuit, one of its effects is a transient change in current. And when I started overcurrent protection, I said that a transient change in current can be regarded as an effect of a fault. That is an effect of short circuit. So we are saying that we are using that effect as an actuating parameter for our relays. So a transient change in the magnitude of current is what we are using as overcurrent protection. We can also have overvoltage protection. We can have frequency protection. I don't know if that's clear.
Yeah, that sounds good. Yeah, sounds good. Yeah.
Okay, now back to this before we had the disruption. Now, someone asked a question. He said, we are saying that if there is a fault here, he's taking this guy out of service. If we are saying this is correct, which is against our objectives, our principles when we come into power system protection. So what he was saying is, a fault at this point should be tripped only by this relay 14. This is the only point of operation we should have in order to prevent selectivity loss.
Excuse me, sir. Your screen is not stable. I don't know if it's from my side or other persons are experiencing the same.
Okay,
I'm unable to see your screen steady.
okay, can anyone see this?
Now I think from my end, yeah, everything seems okay. The screen is stable. Maybe you can check your network.
Okay, I think you should check your internet connection. So the answer to that question is this. As I said earlier, fault isolation is different from relay coordination. If we are looking at fault isolation, then he's right. A fault at lump 7 should not affect the operation of lump 6. A fault at lump 7 should be arrested by this relay at this point. Now, when we talked about relays, we said reliability, the certainty that the relay will operate as at when due. When we come to relay coordination, we are saying that assuming one of the relays does not have the complete qualities required, assuming its reliability is low, assuming the relay does not operate as at when required, we need a backup. Who will back up? So if there is a fault at this point and we are saying this should become a backup relay, we are wrong. That is why this is correct. Now, all these are not operating at the same time. On ETAP software, we can actually see the time of operation of each of the relays. So fault isolation is quite different from relay coordination. Fault isolation, the relay closest to the point of fault should be the one to be tripped. Relay coordination, okay, how would all the relays in the power system network operate, assuming one of them is faulty? That is relay coordination. I don't know if this is clear.
Yeah, it is clear.
Any
Thank you.
question? Okay. In the absence of questions, we can proceed. Now, the crucial need for power system protection cannot be overemphasized, as it helps in protecting the equipment as well as the personnel operating this equipment by isolating the smallest unhealthy portion of the power system network as quick as possible. However, in as much as we use the switch gears, we must have proper settings of these switch gears in order to ensure efficiency and reliability in our protection schemes. At this point, we have come to the end of our session. In tomorrow's session, we are going to be discussing and having much more practical illustration of the software, how the software operates, how we can use the software to design our overcurrent protection scheme, how we can use the software to test our fault isolation to see if what we have designed is actually working, and also how we can use the software to design and test our relay coordination in the system. That is our agenda for tomorrow. We are going to be seeing, okay, what happens when we put the fault here? Is the fault isolated? Okay, if the fault is isolated, if the relay qualities are all working, good and fine. Okay, if the fault is not isolated, what is the backup plan? Is our relay coordination strong enough to ensure sensitivity and selectivity if reliability is compromised? That is what we'll be looking at tomorrow. So, any questions so far?
Yes,
So,
good evening.
if I may, if I
Okay, one at a time.
you can go ahead first. Go ahead first, please.
Thank you very much. My little question is, I have been trying to download each app, the software. I have not been able to find a link for downloading that. So if you have a link or you have the software in a drive or Dropbox, you can kindly share a link for us to download. Thank you.
Okay. For okay, okay, no problem. I will respond to that at the end of the session. Other questions?
Okay, so I just wanted to ask the relays, are they electromechanical relays or electronic relays? The one that trip the breaker once it's getting an information that there is overcurrent, or what kind of relays are they?
Okay, we'll get into that tomorrow.
Okay,
We'll
thank you.
we'll see the selection process. Okay, zone 1, zone 2, zone 3, protection zones of each substation. Let me go into the charts. And someone is asking a question. Okay, when we talk about protection zones, as I mentioned, a protection zone is the part of the power system that is protected by a particular kind of protection. A part of the power system. So if we are talking about zone 1, zone 2, zone 3, if we are segmenting it, then we are saying that, okay, maybe zone 1 is our generator zone, zone 2 is our bus bar zone, zone 3 is our transmission line zone, zone 4 our transformer zone, just like that. However, if we come over to distance protection, zone 1, 2, 3, they mean an entirely different thing. So it depends on the context. Okay? Can power system protection be used to prevent national grid collapse? Okay, the problem of national grid collapse is basically stability. And yes, relay coordination is crucial for stability. Okay, I think people have their hands up. Gideon.
Excuse me, sorry. What do you mean by stability? Do you mean that like there is no much generation compared to
No.
what?
Okay, when we talk about stability analysis, we are looking at disturbances in the grid, disturbances in the system. We can have heavy disturbances, we can have light disturbances. We can have switching disturbances. Okay, let's switch from this source to this source. Okay, let's knock out this load. Let's add this load, addition and removal of loads. So those are disturbances in the system. If there's a fault, maybe a three-phase fault on a bus bar or in a transformer, those are heavy disturbances on a transmission line. So what is the effect of that on the grid? That is stability analysis. How long will it take the grid to come back after experiencing that fault?
Okay. Something.
Generators. What would be the RPM of these generators, the rotor angle? Because once there's a fault, definitely the parameters, the operating parameters will change. So how long will it take these equipment to come back to its nominal operating conditions if they will come back? That is stability analysis.
Okay. Thank you.
Okay, Engineer Ken? Okay, please can you share the slides? Yes, the slides will be shared on the WhatsApp group. The reference network under discussion does not have a cable component. Yes, it was intentional. It's just for illustration, so I didn't want it to be too big. That's why. So it was intentionally omitted. Any other question?
Yeah, good evening, sir. I have a question. Can you hear me?
Yes, we can hear you.
Okay, good evening, my name is-
Okay. This is the last question for today.
Looking at the network, I want to ask if there will be need for coordination between relay 10 and 11. And is the current passing through CB7 and CB8 the same? Is there a difference in current flowing through CB7 and CB8? If there is no difference in current, will there be need to coordinate relay 10 and 11?
Okay, we are actually going to be discussing all that tomorrow. Today's concept was just for the concept. Let's know, okay, is this the right sequence for the trip? Is this the wrong sequence for the trip? And how it's going to trip, we are going to do that tomorrow. How it's going to work out, we'll do that tomorrow. Now, the sessions are being recorded, you will get the recordings, that's one. Then the final question, can we get ETAP software? Now, for ETAP software, we have different versions. To get the latest version, which is version 24 I'm using, which we'll show tomorrow, I'll be dropping a link for that where you can get it. However, the cost is quite high. So if you're not looking at advancing, I can actually prefer a lower version, version 19 for you. And that will come at a cost. I'll share it through my Google Drive and I'll guide you through the installation process and all that, setting it up. But it will come at a cost. So it's going to be quite negligible. It's not going to be a huge amount. So if you need that, you can just send me a message privately on my WhatsApp and we can sort it out. I'll be sharing the link for the updated version of the software, and basically many other softwares are available on the website, so you can feed your eyes. Having said that, we are going to call it a night. Thank you all so much for partaking in this session. Tomorrow we'll have our practical illustrations. Do have a wonderful night, rest.
Thank you, sir.
Thank you. Many thanks.
God
Have a
bless
good
you,
night.
sir.
Bye.
Thank you very